Example 1. TKK Products manufactures electric light bulbs in the 50, 60, 75, and 100 watt range. Laboratory tests show that the lives of these light bulbs are normally distributed with a mean of 750 hours and a standard deviation of 75 hours. What is the probability that a TKK light bulb selected at random will burn more than 900 hours, less than 600 hours, between 750 and 900 hours, and between 600 and 800 hours? Okay, so as I start this off, I have to use the fact that they did give us the mean and the standard deviation as 750 and 75 respectively. Now, these are all x values. I'm looking for more than x being 900, more than or less than x being 600, so forth and so on. I have to be aware that, again, the table gives me a lot, are good for the less thans. The more thans, I have to make sure I'm using symmetry or doing 1 minus the probability of something else, depending on the circumstance. So for the first one, the probability of a randomly selected light bulb lasting more than 900 hours is basically the same as the probability that z is greater than 900 minus 750 over 75, which of course would be 2. Now, using symmetry again, we're looking essentially, for this area here, where z is 2. Meanwhile, if we look at the right spot of the table at -2, I'll have this area. These areas should be the same thing. So that's what I'm noticing here because of the symmetry. Being more than 2 should be the same area as having z less than -2. So I would go to the table now and look up a z-score of -2, which I've done before. It's 0.9772. And so the probability of this is, or less than -2, I should say. I went to the wrong one. Give me a second. Yeah. I went to +2. I should be going to -2. So -2 would be 0.0228. And so that is the probability that I have for that. For lasting less than 600 hours, well, again, I'm looking for this. So I'm going to convert it to a z-score, which means I get the probability of z is less than -2, which is kind of ironic because, I already calculated that, so I expect it to be as well as 0.0228. Between 750 and 900 hours, again, you always want to kind of get an idea of what's going on here. 750 happens to be, the mean. So when I look at the circumstance, between the mean and 900, okay, well, I know that this portion right here is 0.5 because, at the mean, I should be at the 50% point. So 50% should be above, 50% should be below. What I'm looking for is, if I do the probability of being less than 900, I would get this area all the way from here all the way down. But if I take off the 50%, essentially, that goes to the left of 750, that's going to give me the probability I'm looking for. So that's what I mean by sometimes planning it out. Sometimes this picture does help of knowing what's going on. Since the mean is involved, I can just say, okay, well, in this instance here, I'll find the probability that x is less than 900, and then subtract away 0.5 from it. Of course, we've already dealt with the circumstance where x is less than 900. Z would be less than 2 in that instance. That would subtract away 0.5. And being less than 2 gets me back to the table, and I'll go to the positive one now and look up 2, and that's where the 0.9772 comes into play. So when I carry this through, I'm going to have 0.9772 minus 0.5, which is 0.4772. Between 600 and 800 hours. Now here's an instance again, so it's kind of getting off the screen here. But 750 is in between those two. So when I want to do the probability of that, I'm going to do the probability of being less than 800 minus the probability of less than 600, and that should give me what's left in between these two. So That's my strategy. The probability that x is less than 800 is the same as the probability that z is less than 0.67. And the probability that x is less than 600 is the probability is something I've already come up with before because that was part B. That's the 0.0228. That's why you don't see me doing much of a calculation there. And so I look up the 0.67, and I get 0.7486 minus 0.0228, which is about 0.7258.